Simple sum metric aggregates across all dimensions, often masking critical service degradation. When calculating request rates across multiple instances, failing to use group left or group right during binary operations results in Cartesian product explosions or dropped series. To accurately derive per-service error ratios, you must first align the success and failure vectors using explicit label matching. For instance, dividing error counts by total counts requires matching on the service and endpoint labels while ignoring instance-specific labels like pod or host. This foundational vector matching is the primary hurdle system analysts face when moving beyond basic dashboard metrics. We immediately address how to enforce one-to-one or many-to-one matching to prevent data corruption in high-cardinality environments. The by clause specifies which labels must be preserved in the output vector after aggregation. Conversely, the without clause explicitly removes specified labels from the resulting series. Use without when you need a global aggregate but want to retain a specific context label, such as aggregating CPU usage across all nodes while keeping the cluster identifier. When performing binary operations, the on-label matching clause is mandatory for precise control, ensuring the operation only proceeds when the specified labels match exactly between the left and right vectors. Ignoring labels allows the operation to proceed even if those labels differ, which is essential for joining metrics from different sources that share common identifiers but have unique operational labels. The rate function calculates the average per second increase over the entire specified time range. This smoothing effect is useful for long-term trends, but obscures rapid short-lived spikes. The Irate function, or instantaneous rate, calculates the rate of increase based only on the last two data points within the time window. Irate is superior for alerting on sudden critical changes, such as immediate drops in throughput or sharp latency increases, because it reacts instantly to recent data. Always use rate for capacity planning and long-term service-level objective reporting, but switch to Irate when defining alerts that require high sensitivity to transient performance issues. While standard aggregation operators like sum and average work on instant vectors, functions ending in over time operate on range vectors. The average over time function calculates the average value of a metric across all samples within the specified range, for example 5 minutes. This is crucial for smoothing out noisy metrics like disk input-output operations per second. Max overtime is used to identify the peak value reached during a period, useful for determining resource bottlenecks. Remember that these functions return an instant vector, allowing them to be chained with further instant vector aggregations, enabling complex two-stage calculations. Service-level indicators often require P95 or P99 latency, which demands the histogram quantile function. This function operates on Prometheus histogram metrics, which expose buckets representing cumulative counts of observations below specific thresholds. To calculate the 90th percentile latency, you apply histogram quantile 0.9 to the metric mean. Crucially, the histogram must first be aggregated across all relevant dimensions, such as instance and job, using sum before applying histogram quantile. Failing to aggregate the buckets first will result in incorrect quantile calculations, as the function expects a single set of aggregated buckets.
The top K and bottom K functions are essential for identifying outliers and resource hogs. Top K returns the highest K elements based on their current value, useful for finding the top 5 services consuming the most memory. Bottom K returns the lowest K elements, which can identify the slowest performing database queries or the least utilized nodes. These functions are applied after any necessary aggregation. For example, to find the top 3 endpoints by request rate, first apply rate over a 5-minute window, then aggregate by endpoint, and finally apply top 3 to the resulting vector. This pinpoints the exact sources of load. Subqueries allow you to perform an aggregation over a time range and then immediately aggregate the resulting instant vector again. The syntax uses square brackets followed by the duration and an optional resolution, for example, 5 minutes, 15 seconds. A common use case is calculating the maximum 5-minute rate observed over the last 1 hour. This requires calculating the rate over 5 minutes, then using max over time on the resulting range vector over the 1-hour period. Subqueries are necessary when the final aggregation depends on the time series behavior within a shorter rolling window. In distributed systems, metrics can disappear temporarily due to restarts or scaling events, leading to gaps in time series data. The OR operator provides a mechanism to merge 2 instant vectors, prioritizing the left side if a series exists and falling back to the right side if the series is missing. This is often used to provide a default value, such as 0, when a metric is entirely absent. For example, if a service reports 0 errors, the metric might not be exported. Using metric or vector 0 ensures that the series exists with a value of 0, preventing division by 0 errors in subsequent ratio calculations. Beyond simple arithmetic, binary operations offer the unless operator. Unless performs a set difference, returning all series from the left vector for which a matching series does not exist in the right vector. This is powerful for filtering out specific states. For instance, you can identify all running containers unless they are currently reporting a critical error status. This provides a clean way to monitor healthy entities without complex label filtering. Remember that unless requires the same vector matching rules as standard arithmetic operations, demanding careful use of on or ignoring clauses. We combine these techniques to calculate a rolling service level objective for error rates. First, calculate the rate of total requests and the rate of error requests over a 5-minute window, grouped by service. Second, use the OR operator to ensure the error rate vector contains 0 if no errors occurred. Third, divide the error rate vector by the total request rate vector, using onService to ensure correct vector matching. Finally, use AV over time on the resulting ratio over a 1-hour period to smooth the result, providing a stable, production-ready service level indicator that accurately reflects system health.